Good morning. Today we'll see the new topic, that is the filter circuits and its design. So at the end of this particular video, you will able to answer the questions for certain things. What are various filter circuits? How the filter circuits are classified? What are the ideal characteristics of a filter? And how to compare these filters. So for this particular session, what are the objectives we have placed are filter circuit definition and applications, ideal characteristics, then classification and a comparison. So basically, filter term you might have heard with reference to say rectifier circuits. So in a rectifier, in order to remove the AC part from the rectifier, we are using a filter circuit. Okay, so that filter circuit is different from the filter circuits that we are studying. In these filter circuits, the basic objective is to separate the frequency range. So filter circuit in electrical circuits is defined as a circuit which transmits a particular range of frequencies, whereas which stops or which attenuates some other frequency range. For example, if I am having a signal with frequency range 0 Hz to say 1 megahertz, okay, that is the input signal with this frequency range. Now, if I want to have a transmission of a signal from 0 Hz, that is a DC, to say 1 kilohertz, that means in my application, what I need is the signal from 0 Hz to 1 kilohertz only. In other words, what are the frequencies are there above 1 kilohertz, I don't need those frequencies. In this application, we have to use the filter circuit. In another example, if I need the frequencies from say 5 kilohertz onwards up to say 1 megahertz, that means in this second application, I don't need the lower frequencies from 0 Hz to 5 kilohertz. Okay, so I have to use the filter circuits. So these filter circuits are defined as electrical circuit which transmits some frequency range, desired frequency range, and which attenuates other frequency ranges. So in the applications where I need some range of frequencies to be transmitted, to be passed, and some other frequency ranges to be blocked, to be stopped, I have to use the filter circuits. So these filter circuits are characterized with one particular parameter, a specific parameter which is called as attenuation. Attenuation is opposite to amplification. So in amplification, we increase the strength, whereas in attenuation, we have to reduce the strength. That means attenuation stands for opposition. Okay, so when I am listing the ideal characteristics of a filter, then there exists at least one range of frequencies where attenuation is 0. So when I am talking about attenuation, that attenuation constant say alpha, this alpha should be 0 for some frequency range. Okay, and that frequency range we are defining as a pass band frequencies or a transmission band. I will repeat. A filter circuit having one range of frequencies where attenuation is 0 results to a pass band. Okay, so this is the first characteristic of ideal filter. Second characteristic, there exists some another frequency range corresponding to which attenuation constant must be infinite. Okay, that means since the attenuation is infinite, there should be total reduction of the frequencies. So corresponding to alpha equal to 0, what I am getting is the pass band. or a transmission band. Whereas corresponding to alpha equal to infinity, I am getting stop band or attenuation band. So the first characteristic is alpha equal to 0, second is alpha equal to infinity, whereas the third characteristic is related with separation of these pass band and stop band. So there exists one unique frequency which separates pass band from the stop band. Okay, and that frequency is called as a cutoff frequency. This cutoff frequency is a function of the components that we are using in the design of a filter circuit. Okay, one more important characteristic is what are the characteristic impedance is there. We'll define this one in detail. A characteristic impedance should remain constant in a pass band, because in pass band what we expect is a maximum power, maximum output. There must be a transmission of a signal. So in order to match the impedance of the circuit, okay, so this Z0 should be a constant. So any circuit which satisfies these four requirements, four conditions, that circuit is under ideal filters. And these ideal filters, rather these filters are constructed from pure reactances. Okay, that means pure reactances in the sense I have to use inductor, I have to use a capacitor, and the assumption is that inductor, that coil, is not having any series resistance. Similarly, whatever the capacitor I am using, it is not having any dielectric loss resistance in ideal scenario. While designing the circuits practically, we have to select L and C such that their resistances are as small as possible. Okay, that means the filter circuit we have defined as electrical circuit which transmits one particular frequency range with minimum attenuation, ideally 0, which attenuates another frequency range with a maximum attenuation, ideally infinite, and there exists one frequency which separates pass band from stop band. Okay, so these are certain characteristics of ideal filter. Now, depending upon which frequency range is transmitted and which frequency range is stopped, these filter circuits are classified in different categories. Okay, so as far as this classification is concerned, so we will classify the filters based on the frequency range. The filter circuits are classified based on the types of components used. And the third parameter we will take as the characteristics of the circuit. So as far as the first parameter is concerned, frequency range. So given filter circuit transmits which frequency range and it attenuates which frequency range, based on that these filters are classified into four different categories. So if I just separate this one now, the first one is a low pass filter. Second one is high pass filter. Third one is band pass filter. And the fourth one is band stop filter. The special case of this particular filter is the notch filter. That means depending upon our requirement, which frequency range how to use from available signal, the filter circuits are classified like this one. So let us define one by one. So if I am having a low pass filter, how to define this one? Low pass filter. See, you have an electrical circuit. That means if I have this block, and if I want to define this block as a filter, then very first requirement is this circuit should separate frequency range, right? And if I am defining this block as a low pass filter, then specific range at the output I am expecting. Now if you have input signal that is connected here, say this is input signal, and here across a load if I am taking some output, so here I am taking the output, so this V0 is a output. So what I am expecting from this filter is, this filter should transmit lower frequency signals and attenuates higher frequency signals, higher frequencies. Now here lower and higher that are separated with some specific term that is called as cutoff frequency. So if I use the cutoff frequency as FH, this FH stands for higher cutoff frequency of a low pass filter. Okay, so now my definition is a filter circuit which transmits the frequencies up to FH. The term I am using is up to FH. So very clear cut meaning is 0 to FH there is a transmission, whereas the frequency components above FH gets attenuated, gets stopped. That filter circuit is called as low pass filter circuit. So I'll repeat, a filter circuit which transmits the frequencies from 0 Hz to FH, whereas it attenuates the frequencies above FH, that circuit is called as low pass filter. So what this statement is there? This statement I can convert it into, say, a frequency response. So frequency response, which is a very common term used in different electronic circuits, is the response of the circuit for different frequencies. So if I plot the graph of output of the circuit, either output voltage, output current versus frequency, so how circuit behaves for different frequencies, that is represented with the help of a graph, and that graph is called as a frequency response. Response of a given circuit for different frequencies. So here we will have two different graphs. One is, say, ideal graph, another one is a practical graph. That means if I take a filter circuit to be ideal, how the response will be, and for a practical circuit how the response will be. Okay, so if I draw the ideal response first, so let us recall the definition of ideal filter. There exists one frequency where attenuation is 0. Now attenuation is 0 means there is entire transmission. That means whatever the signal is there, that signal gets transmitted. So from 0 Hz to frequency FH, which is called as the cutoff frequency, there is no opposition, no attenuation. That means whatever your signal is there, that signal is transmitted like this one. And above FH, whatever the output is there, that output is 0. Clear? That means here in this range, whatever your alpha is there, this alpha is 0. whatever the frequency range is there above fH, that frequency range corresponds to alpha equal to infinite. So this band, range of frequencies, is the pass band. Whereas above fH, whatever the frequency range is there, available frequencies range is there, that results to a stop band. Whereas a frequency which separates pass band from stop band, that frequency is nothing but the cutoff frequency. And this cutoff frequency is a function of circuit components. So by adjusting the circuit components, I can have desired pass band and a desired stop band. Okay? So this is the practical ideal response of a filter circuit, low pass filter. Now if I just draw the practical response here, again it is the graph of output versus frequency. Now since ideal things never exist in practice, so if I am using circuit components, very certainly there is some opposition. Okay. That means even in a pass band, whatever the attenuation is there, that is not exactly zero. You have some opposition. And because of that, whatever your response is there, that response is like this one. That means with increase in frequencies, if I increase the frequencies from 0 Hertz onward, whatever the output voltage is there, whatever the response of the circuit is there, that decreases. Okay, so that is the practical response. Now if I want to define the cutoff frequency for that particular graph, what I have to do is, whatever the maximum output is there, I have to note that point. Maximum say output voltage, maximum output current, or maximum gain of the circuit. What is the gain? Output divided by input. If I am defining voltage gain, it is the ratio of output voltage divided by input voltage. If I am defining current gain, it is output current divided by input current. If I am defining power gain, output power divided by input power. Actually, power gain term is not the standard term we are using. So there we have to use the conversion efficiency. Okay, so here if I have maximum output voltage, V0 max, if I write there V0 max, then this V0 max is multiplied by 0.707. or 1 by root 2. That means this maximum VO I am multiplying with 0.707 VO max. This 707 is nothing but 1 by root 2. So I am getting the point somewhere down, and from this point if I draw a line, so this line will cut the response here, and again if I draw one vertical line, so this gives your FH. Okay, so what we did, a maximum voltage multiplied by 0.707, we got the point somewhere here, and corresponding to this, whatever the band is there, this band is called as the pass band. Corresponding to this frequency, whatever the band is there, that band is called as the stop band. Okay, that means this is the ideal response of low pass filter, whereas this is the practical response of low pass filter. And once you understood this one, what are the remaining types are there, very easily you can get it. Alright? Okay. So let us move to the next response, next filter circuit, that is say high pass filter circuit. Okay. Now the circuit is high pass. So how to define this one? A filter circuit which transmits frequencies above some critical frequency. Above some critical frequency, there should be a transmission. In other words, a filter circuit which attenuates lower frequencies, that circuit is called as high pass filter. Okay, that means in case of low pass filter, there is a transmission up to FH. Now here I will write the term from FL. Okay, try to get the point. A filter circuit which transmits the frequencies from FL onwards is called as high pass filter, where FL is a lower cutoff frequency of high pass filter. Now if I want to draw the waveform, once again we will prefer that frequency response. So this is the graph of output voltage or gain versus frequency, right? So if here the point is FL, what is FL? A lower cutoff frequency. So this is 0 Hertz. So this high pass filter will transmit frequencies from FL. Okay, that means from FL there is a transmission, whereas up to FL, 0 to FL, there is no output, there is no transmission. Okay, so corresponding to this one, your output is 0, whereas corresponding to this range, you have the transmission. So that's why this band, all the frequency components fall under the range pass band. And ideally for pass band, alpha is equal to 0. Whereas between 0 to FL, there is a stop band, no rejection, attenuation band, corresponding to which alpha is equal to infinity. And what are the FL is there? This FL is a lower cutoff frequency of high pass filter. See, the notation is L because it is the lower frequency, lowest possible frequency from which a transmission is there. Now if I just draw the practical response of the same filter, so once again it is the graph of output voltage versus frequency. So initially you have stop band. Ideally there is complete rejection, but practically there is some signal that is transmitted. Okay, that's why even in a stop band you are getting some output, and as you increase the frequencies, what the output is there, that output increases and then afterwards it attains the steady level. Okay, that means corresponding to this one you have maximum output. So I can write a VO max. Right. Now how to separate the pass band and stop band? So what is the procedure we have used for low pass filter? Exactly the same procedure we have to follow. How to do? Multiply this maximum gain, maximum output voltage by 0.707. So how 0.707 VO max. Okay, so that point is somewhere here. Say, then I will draw one horizontal line. So that horizontal line cut the response at this particular point. Then from this I have to draw one vertical line. So this point is nothing but FL. Okay, so this FL separates your pass band and stop band. Okay, so corresponding to this one you have pass band, whereas corresponding to this one you have stop band. So practically here alpha is large, practically here alpha is very small. Okay, so that is the basic difference between ideal response and a practical response. Okay, that means just if you read this term low frequency, transmission is there for low signal. If you read this high pass, transmission is there for high signal, high frequency signal. Like that, when we are having this type of filter, band pass filter, a filter circuit which transmits some frequency range. See, a filter circuit which is transmitting some frequency range. Outside that range there is attenuation. That filter is called as band pass filter. Okay, so our next type is the band pass filter. So the third type is band pass filter. So to define this filter once again, it is an electrical circuit which transmits some desired frequency range. If I call that desired frequency range as F1 to F2, F1 is the lower frequency, F2 is the upper frequency, then F2 minus F1 is the desired band which is to be transmitted. So corresponding to F2 minus F1, I am having pass band. Okay, that means I am interested only for the frequency range F2 minus F1. In other words, outside this range there must be attenuation, there must be rejection. That means for this particular band pass filter you have one pass band whereas you have two stop bands. Okay, so the same thing if we represent with the help of graphs, frequency response, again it is the graph of output voltage or gain of the circuit versus a frequency. So ideally there should exist a one frequency band now. That means there should exist some range corresponding to which attenuation is 0. Okay, that means here alpha is equal to 0. There should exist some another frequencies that is between 0 to F1 and F2 onwards, corresponding to which there is no transmission, that means alpha equal to infinite. Okay, so what I got is one range where alpha is equal to 0, straightway I am getting the pass band, and when alpha equal to infinity I am getting stop band. Here also I am getting stop band. Whereas this F1 is called as a lower cutoff frequency. And this F2 is called as upper cutoff frequency. Okay, and F2 minus F1 is your pass band. That means that particular range of frequencies are available at the output. So this is the ideal response. Now if I draw the practical response, so here is the frequency, and here you have the output voltage. What will happen here? You don't have a circuit with alpha infinite or alpha equal to 0. That's why whatever your response is there, that response is like this one. So it increases, then afterwards it decreases. Okay, so what is this middle portion is there, corresponding to which gain is or the output voltage is almost fixed. Okay, so I will write this as the maximum point, V0 max. I will multiply this V0 max with say 0.707, so it is 0.707 V0 max. So just draw one horizontal line. That horizontal line cuts here at two distinguished points. So this point which is closer to 0 is F1. This point is F2. Okay, and corresponding to this one, what I am having is the pass band. So one pass band between F1 and F2. Between 0 to F1 I am having stop band. Above F2 again I am having a stop band. Okay, so the filter circuit which transmits desired frequencies whereas attenuates outside the frequencies, that is outside that particular range, is called as a band pass filter. Now the last one is the band stop filter. So just opposite, a filter circuit which